Greetings, everyone. This is Rifat Sipahi, and from Northeastern University, Mechanical and Industrial Engineering. And today I would like to provide you a brief introduction to heliostat control problems. And we will focus on this control problem in the context of ME 4555 System Analysis and Control course. And first of all, what is a heliostat? And let's just get started with that. And before I even start with that, I would like to state some of our objectives in this demo and within the homework. First of all, understanding and appreciating how heliostats work and what are some challenges there. And then in the context of the course, design of PID controllers with pole placement and MATLAB PID tuner, and understanding the trade-offs between speed of response, actuation magnitude, and power consumption, and investigating some noise sensitivity problems using Bode diagrams. So the overall approach from 1 through 4 comprises the following. We'll start with a single degree of freedom dynamical system and obtain a transfer function. And then the approach will be to develop closed-loop system pole transfer function and perform a pole placement. That's what the students will be doing. And then the students will build a simulating model, and I'll show you an example of that in a moment. And they will utilize the MATLAB PID tuner to refine the PID gains that were originally designed at step 2. And then at step 4, there's going to be some investigation of noise and tracking error relationship using Bode command in MATLAB. What is a heliostat? Many of you may have seen this. For example, there are capstone projects happening in the department on these topics, but imagine that you have an heliostat, which is a huge panel that has that is able to reflect the solar rays and with proper orientation of its angles, it's able to focus these solar power on a central location where the energy can be harvested from actually an array of these reflective mirrors and to harvest solar energy. Now, there are a lot of interesting problems and challenges with this design, and for example, the angular displacement of the heliostat has to be really perfect to be able to reflect the sunlight to the receiver and focus this properly. So any small angular deviations can actually reduce the performance of the energy harvesting effort. And then to that end, how does one know exactly what the angle should be? So there must be some type of sensors and instrumentation at the receiver end, and that can tell the heliostat whether or not its angles are correct. And imagine you have many of these heliostats. How would you do that properly? So you can actually collectively orient these, let's say, mirrors to focus the sunlight with the most optimal manner. Now, to this end, and within this course, one of the goals is to investigate or to understand the control challenges associated with what's one single heliostat. And you may imagine that the heliostat now is like a panel, right, that has an elevation axis and an azimuth axis. And one would need to control both of these angles to be able to reflect the sunlight in the right direction. And in general, the equations of motion of such a 2 degree of freedom system is actually can be quite complicated, especially if it moves really fast. But it doesn't, and given the motion of Earth relative to the Sun is not super fast, these angles need to be updated and changed very gradually. So one can actually make some assumptions in the sense that the azimuth motion and elevation angle motion actually can be what we call decoupled. What I mean by that is, in general, the elevation axis and the angle phi changes the mass moment of inertia around the azimuth angle. So there's a coupling. Imagine that this also can cause dynamic coupling, but in the case of slow motion, this coupling can be ignored. And so what one can then consider this to be 2 decoupled dynamical systems, one associated with the azimuth angle. So in that first equation, only psi appears, but not phi. And the other one is concerned with the elevation angle, in which only phi appears, but not psi. right? And J represents, denotes, J's denote the mass moment of inertias. B, you can consider those to be viscous damping, and then T1 and T2 are the torques that are needed to generate the motion. Given both of these dynamics have the same structure, right? There's actually no need to study both of them. We can just study one of them to understand what are the control challenges. So that's what we're gonna do. But before we go forward, I would like to show you an animation of this that you can actually create in Simscape, or if you would like to see the file, just send me an email. I can provide the file to you. And I create a little sphere here that represents the sun. Imagine there is no movement of the base of the heliostat here, but I'm just trying to give you a sense of how the heliostat position in azimuth and elevation could be controlled to potentially to track the sun relative motion with the Earth's relative motion with respect to the sun. And we're not going to really do a lot of this type of 3D animations in this activity, but what you actually will gather from this could be applied to an animation of this type. All right, so let's go ahead and have a look at the simplified version. And just to keep the angle generic, I call that theta. And imagine we have a panel, and its center of mass is supported at the fulcrum, free to rotate, but there is maybe some viscous friction, and you want to lift this with a torque T. And so equation of motion, assuming that in this case the mass is perfectly balanced or held up is taken up by the fulcrum point, the pivot point, the gravity effects disappear, and then our goal is to investigate how much torque is needed to able to regulate the angular displacement of this inertia with mass moment of inertia J and with some viscous damping B at the pivot. Okay, to this end, what we will do is we'll actually write down the transfer function of this dynamics between torque and angular displacement, which is in this form, right? We set initial conditions to 0. And now we have the open loop transfer function between torque and angular displacement. And then we can put that in the context of a PID controller as shown here on the top. So now we have a closed-up system between a reference angle that needs to be satisfied versus the actual angle of the system, and the difference between them is the error that a PID control will process to compute how much torque is needed to drive the dynamics towards the theta goal. Here, the details of these questions will be available in the homework, so there's no need to actually repeat this here, but in question 1, we'll be showing that the closed-up dynamics respects the transfer function given here. At the end, the overall idea is going to be really investigate the closed-up system and design PID controllers so that the closed-up system has particular pole values in question 3 are given here, or a different set of pole values is given here. And what difference does it make if the pole settings are different is some of the things that you will be investigating. And to this end, one maybe here a clue I would like to give you is that G of S given in this particular form, you can actually consider it as 2 separate transfer functions that are multiplied back to back. And with simple relationship, you will discover that the variable before 1 over S must be angular velocity. So what happens is you apply torque, it's converted to angular velocity, and that's converted to theta variable. So actually, I have a short YouTube video here that you can watch to understand how to get some clues about how to solve question 6. And actually, I am building this block diagram in the Simulink in the YouTube video and in Simulink and demonstrate how to read the torque values. So hopefully that YouTube video will be useful. And going forward, I have another YouTube video you can use to get yourself familiar with how PID tuner works in MATLAB Simulink. So please have a look at that. That will give you all you need to be able to answer the PID tuning question at question 7. And lastly, what you will do is you will investigate if for some reason the reference signal is not a perfect step function, but if it's actually cyclic. Now, in this problem, we are assuming that this reference signal is arriving from some algorithm, right? And that determines what angle is better for the heliostat, for, let's say, for better energy harvesting purposes. So, but this signal doesn't have to be a step function. It may end up being cyclic, and or at least it must be studied for cyclic inputs, because sometimes oscillations may also arise in the feedback line due to, for example, noise and other reasons that oscillation may propagate around the loop. For that reason, it is really important to understand how the commanded angle oscillations could potentially put the output angle theta into resonance. So to this end, and knowing that this is a closed system transfer function, you will be actually applying the Bode diagram of this function for some given PID gains. Actually, I set the I gain to 0 for simplicity. And you will be obtaining phase and gain margins that are really critical metrics associated with the stability of the system. And then you'll be discovering some frequencies associated with the input signal, right? Such that when the reference cycles at those frequencies, it will make the output resonate, meaning the output amplitudes will be larger than input amplitudes. Through the Bode diagrams, you will actually discover what this frequency range is, and then you're going to pick a frequency from that range and show in simulating indeed that the output actually produces oscillation amplitudes that are larger than the input oscillation amplitudes. And with that, the homework exercise will finish. Of course, an instructor may decide to use only some of these questions within a homework setting. So expect to see maybe all or some of these questions within the homework setting. But I hope this presentation was useful. So even if you are not potentially assigned all the questions, you can always give it a shot and solve these questions. And always, anytime, reach out to me if you have any questions how to approach these problems. Thank you.